Okay, so welcome everybody to this first talk on PEX point theory. So it's always great, of course, to see such an enthusiastic audience. And today I'm going to be the moderator of the session. So let's set a couple of rules to maintain the decorum and to get maximum benefit in this short interval of time. I would request everybody to turn up their microphone. And in case of if you want to ask question, first of all, let's keep it to the end. And in case if it is very important, you can raise your hand and upon the preference of the speaker, turn on your microphone and ask the question. So today our speaker is Dr. Wahidullah. He had done his master and PhD from Qaidism University, Islamabad, Pakistan, while focusing on PEX point theory and Banach algebra. He had also participated in the postgraduate diploma program of International Center for Theoretical Physics, ICTP. Currently, he is doing a PhD from the University of Trieste, Italy, where he is focusing on the qualitative theory of ordinary differential equation. I have the privilege of talking to him on many mathematical, social, religious, and political issues, and he has been always a guide to me. So I hope we will learn a lot from him in this short interval of time. And on the behalf of the team of Maths Volunteer, I welcome you, Wahidullah, to this very amazing group of guest speaker. And over to you.
Okay, thank you very much for your introduction, and thank you all the team members of volunteer groups. Okay, let me just share my screen. Can you see my screen, Rizwan?
Yes, we can.
Okay, thank you. This talk is about metric fixed point theory. Fixed point theory is a very large field, so one cannot explain everything in 1 hour in fixed point theory. So I will more focus on just Banach fixed point theorem and some of its applications, and also some other relatively contractions which are important for the research purpose of it. The layout of my presentation will be the following. I will start from a well-known Banach contraction principle, and then I will give some simple applications of these theorems. In the third section, I will present some generalization and some other contractions which are parallel to Banach contraction. And at the end, I will give some extension of a metric space, which we call metric type spaces, but which are not metric spaces. Now, before going to Banach contraction principle, it is important to know that what is a fixed point of a map. If we have a non-empty set and T is a self map, a point X is said to be a fixed point if T of X equal to X. From the example, we can see that if we define from R to R, T of X equal to X by 2, for every X belongs to R, then X equal to 0 is the fixed point of T. Geometrically, it means that those points of a domain is a fixed point of a map T if it intersects the x-axis, the identity map, the graph of identity maps. Sorry. Here you can see that if we define a map, this is the graph of a map. This one is just a parabola x square. So if we define T of X equal to X square, then this point and these points are the fixed point of this map. As you can see that T of 0 equal to 0 and also T of 1 equal to 0. and also T of so these two, if you can see here from the graph that this intersects the line y equal to x, means it intersects the graph of identity functions. Similarly, if we take the functions which is called x cube, this is the graph of function x cube, then you can see that this point, and also this point are fixed point of the map T of x equal to x cube, because it intersects the graph of identity function. And there are functions which has infinite many fixed points. This is the graph of a function which is somehow I have plotted in a computer. So it means intersects. You can see that if we take a x absolute function, that this is the graph of x absolute, and the blue one is the graph of y equal to x, means identity functions. Here you can see that all these points are a fixed point of the map T of x equal to x absolute. Now, if means I define x absolute plus 1, then the graph somehow becomes something like this. And you can see that it cannot intersect the graph of identity function. So these functions, if I define f of x equal to x absolute plus 1, then this function does not have any fixed point. So there are means functions which does not have any fixed points. Now I would like I hope that everybody knows what is the definition of a matrix space. So I will not recall this definition because it is very elementary. If we have a matrix space and there is a map T from X to X, a self map, then the map T is called a Banach contraction if there exists alpha belongs to 0, 1, which satisfies condition 1, which means that distance between the images is less than or equal to alpha time distance between the points. And the smallest alpha for which the inequality 1 holds is said to be Lipschitz constant for the map T. Here is I have given one example that let R be a matrix space where D is the Euclidean matrix. Euclidean matrix is D of x y equal to x minus y absolute. Then and T of x equal to x by 2, then T is a contraction on R with alpha equal to 1/2, because if we apply T of x minus Ty, then it becomes x by 2 minus y by 2, and we can take common 1/2 to get that this is less than or equal to 1/2 x minus y. I have mentioned that we will define an R Euclidean matrix which is just absolute of its values. Now this is the famous Banach contraction principles. Banach proved this result in his PhD thesis while he was working on the existence of solutions of integral equations. So basically, the idea was from existence of solution of integral equation, because almost every physical phenomena goes to differential equation, and in some time it is difficult to find the solution directly of a nonlinear differential equation. So you will need to take means alternative of differential equation, which is a integral equation. The statement is the following, that let XD be a complete matrix space and T be a contraction mapping on X. It means that T satisfies the above properties, then T has a unique fixed point X. And for each X0 belongs to X, the iterative sequence Xn equal to Tn of X0 converges to X. Here the iterative sequence, you can say that if you have X0, then you can define Tx0 will be belongs to X. So means you can define that X1 equal to Tx0. Now Tx0 is in X. So if I apply again T, then t square x naught will also belongs to x. So I put that this is a x2, and similarly we can define that x3 equal to t cube of x naught, which is a t of x naught, and so on. The idea of the proof is constructive, which means that we will construct some sequence and then show that this sequence is a Cauchy sequence, because in the statement we have the hypothesis is that the metric space is complete. So what does it mean? That if every Cauchy sequence in a metric space converges, then we say that this metric space is complete. So if we are taking some assumptions, then it means that we will use these assumptions. Now we will construct a sequence, then we will show that this sequence is a Cauchy sequence, and use the hypothesis that this sequence is converged to some point. Then we will show that this point is a fixed point and also a unique fixed point. Now, as I have shown in the previous page, that we can construct a sequence in this way, that x naught, x1 equal to tx naught, x2 equal to tx1, which is t of x naught, and so on, xn equal to tn of x naught. Now, the idea is to show that this sequence is a Cauchy sequence by using the given hypothesis. But by 1, which is the inequality of contractions, we can write that d of xm plus 1 comma xm will be equal to d of t m plus 1 x naught comma tm x naught. So, which is equal to d of t xm comma t xm minus 1 by the definition of the sequence. And this is less than or equal to by 1. 1 is the contraction inequality, that this is less than or equal to alpha time d of xm comma xm minus 1, because we know that it satisfies for every xy. So it will satisfy for xm and also xm minus 1. Now, this sequence we can write that this is equal to alpha d of, again by this definition, that the construction of the sequence, we can write that xm is just t of xm minus 1 and xm minus 1 is t of xm minus 2. So again by using 1, this is alpha. 1 alpha is here. Again multiply by 1 alpha, it becomes alpha square t of xm minus 1 comma xm minus 2, again by using the contraction inequality. And we can say that this process will go, and at the end we will stop on this, that alpha power m d of x1 comma xn comma x naught. So we stop here, that d of xm comma xm plus 1 or d of xm plus 1 comma xn, which are both equal in the sense of metric, is less than or equal to alpha power m d of x1 x naught. Now for n greater than m, by triangular inequality, which is nothing but this, that d of x was z is less than or equal to d of xy plus d of yz. Now here I have used generalized, which means that I have taken not just 2 elements, I have taken a finite n elements. For n greater than m, d of xm or xn will be less than or equal to d of xm comma xm plus 1 plus d of xm plus 1 comma xm plus 2 plus up to so on. The idea is this, that d of xm comma xn is less than or equal to d of xm comma xm plus 1 plus d of xm plus 1 comma xn. First, in the first step, we will do like this, by triangular inequality, we can write this. Now, this inequality can again be write that this is less than or equal to d of xm plus 1 comma xm plus 2 plus d of xm plus 2 comma xn, and so on. We will get that this is less than or equal to d of xn minus 1 comma xn. Now this is now we will use the inequality on the previous page, which is the d of xm comma xn plus 1 is less than or equal to alpha time alpha power m d of x1 x naught. So here I will use that this is less than or equal to alpha power m d of x naught x1. But here I will use that this is less than or equal to, in this line, this is xm plus 1 comma xm plus 2. So I will write that this one is less than or equal to alpha power m plus 1 d of x naught x1, and so on. At the end I will write that this is less than or equal to alpha power n minus 1 d of x naught x1. So d of x naught x1 is common. We have just common this and write the other as a sequence, as some other sequence, which I have denoted that sk equal to summation k start j start from 0 to k alpha power j. Now what is sn minus sm? Means if we write this Sn will be equal to alpha 1 plus alpha square plus up to so on alpha power m plus up to so on alpha power n, because we have taken n is greater than m, and Sm equal to 1 plus alpha plus up to so on alpha power m. Now what is Sn minus Sm? Sn minus Sm minus 1, here we can write that this is Sm minus 1. So it will be equal to alpha power m plus alpha power m plus 1 plus up to so on alpha power n. Now if I denote this series S equal to j start from 0 to infinity alpha power j, then we can see that it is just a geometric series. But we know that this alpha is less than 1. We have given this that t is a contraction with alpha between 0 1. So alpha is less than 1, and hence this series converges. By just elementary mathematics, we can say that this series converges to some points. So it converges, which implies that the sequence of partial sum, and by definition of a convergent sequence, we can say that the sequence of partial sum sk converges to S, which means that limit k approaches to infinity, sk equal to S. Now n is greater than m, so if m approaches to infinity, implies that n will also approaches to infinity, and hence we can say that limit m approaches to infinity, Sm will be equal to S, and it will be equal to Sn, and hence we obtain that limit nm approaches to infinity d of xm or xn equal to 0. Why? Because if we go on this page, here what is the last inequality? The last inequality is that d of xm xm or xn is less than or equal to Sn minus Sm d of x naught x1. Now if I take limit nm approaches to infinity both sides, then it becomes xn or xm is less than or equal to limit n approaches to infinity Sn minus limit m approaches to infinity Sm into d of x naught x1, which is independent of n, so we can take outside. Now this one is equal to S, and this limit also equal to S, so it becomes S minus S d of x naught x1, and which is equal to 0. And it means that this limit nm approaches to infinity is less than or equal to 0. But we know that by definition of a metric space that this cannot be less than 0. So it must be equal to 0. Or you can use the first property of a metric, that d of xy is always greater than or equal to 0. So this one is also greater than or equal to 0, and hence you can say that this limit equal to 0. And what does it mean? If this limit equal to 0, then we can say that this sequence is a Cauchy sequence in X, but X is complete. We know that by hypothesis that X is a complete matrix space. So if we have a Cauchy sequence, then it must be converged to some points. And we say that there exists some X belongs to X such that Xn converges to X. The second step is to show that this sequence, the second step is to show that this point X is the fixed point of the map T. Now, if we see from the contraction inequalities here, the map T is a contraction, and we can see directly from one that if a T satisfies condition 1 with alpha belongs to 0, 1, then T must be a continuous function, because here you can also try that if I take Xn converges to X, then what does it mean that D of Xn wa X converges to 0. Now, D of Txn wa Tx is by definition less than or equal to D of Xn wa X comma alpha. But if this converges to 0, then what does it mean? That this also converges to 0, and it means that T of Xn converges to Tx. And since this is a matrix space, so we can say that a T is a continuous map. So if we have a contraction map, then it must be a continuous map. Now we will use this continuity of the map T here to show that X is a fixed point. Since Xn equal to T of Xn minus 1, we can write that X equal to, by definition of convergence sequence, since Xn converges to X, so we can write X equal to limit n approaches to infinity Xn, which is equal to limit n approaches to infinity T of Xn minus 1. But this T is continuous, so we can inside the limit T of limit n approaches to infinity Xn minus 1, and we know that if Xn converges to X, then every subsequence of Xn also converge to X in a metric space. So this sequence will be also equal to X, and hence T of this equal to T of X, which shows that X equal to T of X, which means that X is a fixed point of the map T. And finally, we need to show that this fixed point is a unique fixed point. And for this, we will take a contradiction method, and we will assume that let X and Y be two fixed points of T. Then by definition, T of X will be equal to X and T of Y will be equal to Y. And now by contraction inequality, we can write that T of XY equal to T of Tx comma Ty, because Tx equal to X and Ty equal to Y. And this is less than or equal to alpha time D of X minus Y, which implies that now if we take this on the left side, then it becomes that D of xy minus alpha time D of xy less than or equal to 0, which implies that D of xy is less than or equal to 0 divided by 1 minus alpha, which is equal to 0, since alpha is in between 0 1. But D of xy is greater than or equal to 0. So D of xy equal to 0, which means that x equal to y. And what does it mean? It means that we cannot have two fixed point. We will have unique fixed point, and this is the proof of the Banach contraction principle. Now I will go to some applications. For the application point of view, I will first take one example which is somehow trivial, that if we define T on R by Tx equal to x by 2, then we have D of Tx or Ty is equal to 1 over 2x minus y, which we can write that this is less than or equal to 1 over 2x minus y. So this is it satisfies the contraction inequality, and R is we know that R is a complete metric space with Euclidean metric. Now here is the graphical meaning of the contraction principle, that if we take x naught equal to 32, then its image is this one, which is 16. I have write this that t of x naught equal to 16. Now what is 16? 16 is here. If we again apply t, then it gives us this point, which is equal to t. It means that t square of x naught equal to t. And sorry, 8. And 8 is this point. So if again we apply t, then it gives us this point, which is 4. It means that t cube x naught equal to 4. And again, if we again apply t, then it give 4 is this one. So again apply t4 of x naught, which is t4 of 32, is equal to 2 here. So we get 2, and if we again apply on 2, then it gives us 1, which is this one. So if we again apply t, then it gives us 1/2. 1/2 is this one. Sorry, 1 was this. 1/2 is this one. It implies that t6 is t6 of x naught equal to 1/2. And again apply, it will give us that t7 of x naught is just 1 over 4, which is equal to 0.25. And you can see from the example that it goes to 0, means there at 32, it was a 16, then 8, then 4, then 2, and so on. It goes to 0. Similarly, if you means apply it on minus 32, then it will give you minus 16. Again, by minus 16, it will give you minus 8. And again, by minus 8, it will give you minus 4, and so on. So you can see from the graph that it goes to 0, to the origin. And from the example, you can also see that t of 0 equal to 0 by 2, which is equal to 0, which means that 0 is a fixed point of the map T. And this also means you can say that this is the example of a contraction, that what contraction actually do, what contraction actually does graphically. So if it contracts the distance between the images, now I would like to discuss some applications in the existence and uniqueness of solution of a certain first order initial value problem. If we take the initial value problem 3, which is just y prime t equal to f of t, y of t, where f is from I cross Rn to Rn, and I have taken here 0b. If f is continuous, now if this f is continuous in t and y, and what does it mean? That this is continuous, and it means that y belongs to C1 of I. C1 of I is the space of a continuously differentiable function defined on I. Means this space is the set of all those functions which defines from I to R and continuously differentiable, and which means that it is differentiable and its derivative is also continuous. Now here we can see that y belongs to C1 of I. Solve equation 3 if and only if y belongs to C of I. C of I is just the set of continuous functions defined on I, which means that those functions which define from I to R and are continuous. Now y belongs to C1 of I will solve 3 if and only if y belongs to C of I, which is continuous. Equation 4, which is an integral equation. And you can see here that if I directly integrate, I just integrate this equation, then I can get this equation. Because if we integrate from 0 to t both sides, then by the theorem, fundamental theorem of calculus, we get that this is y of t minus y naught equal to 0 of integral from 0 to t f of t y of s ds. Now I have just put y naught on the other side. Y naught is y of 0. Now if we define an operator t from a set of continuous function to itself by t of y and define as for some t that t of y of t equal to y naught plus from 0 to t integral from 0 to t f of s y as d of s. Sorry. Then the equivalence above is expressed briefly by y salo 3 if and only if y equal to t of x. Now here you can see that if y, we have this, that if y salo 3, then y salo 4. Now, what is this map? This is an operator t. If y equal to t of y, then what does it mean? That y of t will be equal to this. And it means that y salo 4. So, the equivalence becomes that y salo 3 if and only y is a fixed point of this operator. And we will show that this operator has a fixed point if there is some additional hypothesis. The theorem is this, which is application of the Banach contraction principle, that if f is continuous and also Lipschitz in y, which by definition, which I have discussed, that if there exists some L greater than 0, such that f of ty1 minus f of ty2 is less than or equal to L time y1 minus y2, then there exists a unique y belongs to C1 that follows equation 3. The idea is to use the Banach contraction principle, and for Banach contraction principle we need two things. One is a complete metric space and the other one is a contraction map. So we will show that we will show that this is a complete metric space, and also show that this map T satisfy a contraction inequality. We observe that we can see that C of I is a Banach space. Sorry, here we will first define some norm on this space, which is defined as follows: y norm L equal to supremum of t belongs to I e power minus LT y of t. Now we will show that this is a norm space and then show that this is a Banach space. And we know that every norm space is a metric space, because if we have a norm, then we can define d of xy equal to x minus y norm. Now, if we show that this is a Banach space, then it implies that it is a complete metric space. Since this norm YL is equivalent to Y infinity, that's I will not prove, it's very easy. You can see just by the definition of this norm that this is equivalent to infinity norm. What is infinity norm? Infinity norm is Y infinity equal to supremum of y of t absolute, where t belongs to I. But here I is a compact interval, a closed and bounded interval, so we can take supremum as a maximum. So you can means show yourself by yourself that this norm YL norm is equivalent to y infinity norm. And since y infinity norm is a complete norm, which shows that this space C of I is a Banach space with respect to infinity norm. Hence, by use of equivalence, that if we have two equivalence norm on a sum space X and on with respect to one norm, the space is complete, then with respect to another one will be also complete this space. So we show that this implies that C of I is a Banach space, which implies that C of I is a complete matrix space. Now we show that T is a contraction, and to show that we take zy, two elements of C of I, and notice that T of y of t minus T of z of t will be equal to f of s of y of s minus f of s z of s ds, because y naught and the other y naught will be got cancelled, y naught minus y naught, and it will be cancelled. Thus, for all t belongs to I, we have this inequality that e power minus lt ty minus tz of t absolute is less than or equal to e power minus lt. I have just taken absolute, but then we know that this is a means elementary, that if we have integral dx, then this is less than or equal to f of x absolute integral. So I have used this, and then I have multiplied e power ls into e power minus sl, which will not affect the integral. And the other one I have used this means if it is in absolute, then it satisfies this inequality, and I have used just this inequality and then takes a maximum or supremum on both sides. Then we get that this is less than or equal to y minus z norm L, and the other one, this one is minus ls, will is due to this norm, that y norm equal to supremum of this e power minus lt y of t. So here we got that this is 1 minus e power minus lt y minus z norm L. But we know that t belongs to 0 and b. So this is less than or equal to 1 minus e power minus lb. This is elementary. You can means show you by yourself. Thus we get that ty minus tz norm. Now if we take supremum both, if we take supremum over t both sides, then we get on this side that this is equal to ty minus tz norm L, and this is less than or equal to, and this we do not have something, so it will not affect 1 minus e power minus lb y minus z norm L, which is this. But here we have noticed that if we take alpha r k equal to 1 minus e power minus lb, then this is less than 1. And this shows that this is less than some alpha r k y minus z norm, which shows that t satisfies the contraction inequality. And hence, by Banach contraction principle, this t has a unique fixed point. But if we see the structure of t, then we can say that if this is means if it has a unique fixed point, that what does it means? That there exists some y such or u such that t of y equal to t of y equal to t of y, which means that y equal to y naught plus this, which means that y of t will satisfy this condition, and which means that it will satisfy 3. And hence we can say that this unique fixed point of t is actually this unique solution of 3. Now I will discuss some other generalization of a Banach contraction. Let x dv, which is means this theorem is by Edelstein. So let we have a compact matrix space and t from x to x satisfying this contractive inequality. This inequality is said to be contractive, not a contraction. then T has a unique fixed point in X. Because there are some functions here we have this example that it satisfies this inequality 5, but it does not have any fixed point because the map domain R is not compact. This map, because if we take that Tx, if it has a fixed point Tx equal to x, then this implies that x equal to natural log of 1 plus e power x, and by taking both sides exponential function, it implies that e power x will be equal to 1 plus e power x, which implies that 0 equal to 1, which is not possible. So we get contradiction that T has a fixed point. So this map does not have any fixed point, but it satisfies the inequality 5. You can use mean value theorem to show that it satisfies a fixed, it satisfies 5. Here means you can take that this map is a continuous map and also it is differentiable. So if there exists, and it's what is its derivative? Its derivative is T prime x is equal to 1 divided by 1 plus e power x, which is less than 1 for every x. It means that derivative of t is less than 1. So if you use a mean value theorem, which is somehow, let us use that there exists some c belongs to, means if I take this on some specific interval, then there exists some c belongs to minus infinity or plus infinity, such that t prime c will be equal to, or sorry, here I can take a b t of or xy, means you can say t of b minus t of a divided by b minus a, and it implies that t of b minus t of a absolute is less than or equal to b minus a absolute for all a b belongs to R. So it satisfies this inequality 5, but it does not have fixed point because this map R is sorry, the space R is not compact. So if map is a compact and it satisfies the contractive inequality 5, then it will have a unique fixed point. The proof is very short. As d and t are continuous, so if we define f of x equal to d of x tx, then this map attains its maximum and minimum by a theorem in topology, that if a domain is compact and f is continuous, then it will attain its maximum and minimum. So if I take x naught be the minimum value of f, then this x naught will be a fixed point, because if x naught is not a fixed point, if it is not equal to tx naught, then by 5, which is contractive inequality, we have f of tx naught equal to d of tx naught comma t square x naught, which is less than d of x naught comma tx1, and this is equal to f of x naught. So we got contradiction because we have said that x naught is a minimum point, and here we have showed that tx naught, f of tx naught is less than f of x naught, which means that tx naught is a minimum, which is not possible. Hence our contradiction is wrong and x naught equal to tx naught. Again, if we have two fixed point, then by using the same inequality, it is not, we can get that tx naught y naught is less than tx naught y naught. Now, if I have shown that this is another generalization of a Banach contraction, that if we have a complete metric space and T satisfies this inequality, where phi is any monotonical non-decreasing function such that it satisfies this limit. Its limit phi n of t equal to 0 for any fixed t. Then the map T has a, here it is not less than 0, it is greater than 0. Then the map T has a unique fixed point, and for every iterative sequence, and for every x naught, the iterative sequence converges to U. If we take phi of t equal to LT, then we get directly the Banach contraction principle. You can see that if phi of t equal to LT or some alpha t, then this is just alpha time dx xy. So we get exactly the Banach contraction. I will not prove this. There are some other contractions which are parallel to Banach contractions. And the idea is that the Banach contraction principle was just for continuous map. So Kenan in 1969 introduced another contraction which also apply for non-continuous maps. Let XD, it is not means a generalization, it is somehow parallel contractions. Let XD be a metric space. A map T is said to be a Kenan type contraction if there exists some real number between 0 and one half, which satisfies this inequality. Means that d of tx ty less than or equal to k time dx tx plus d of y ty. This is the example one given. We have one example that if we take x equal to 0, 1, closed interval with usual metric and t be defined by this way, we can see here that it is not a continuous map. So we cannot use, so this is not a Banach contraction because we have proved that Banach contraction is a continuous map. Similarly, contractive mappings are a continuous map. But this map is not a continuous map, so we cannot use a Banach contraction or a Edelstein contractive theorem. Here, why this is not continuous? Because the limit x approaches to 1 is x divided by 1 divided by 16, which is not equal to t of 1, which is 1 divided by 18. Now we will show that it satisfies these contractive inequalities. I have shown this direct. Then we if we take x, y both belongs to 0, 1, but not equal to 1, means this is open and from 0 side it is closed. Then tx minus ty will be, tx will be equal to x by 16 and ty will be equal to y by 16, which is equal to this. And x minus tx will be equal to x minus x divided by 16, which is 15x divided by 16. Similarly, y minus ty, 15y minus 16, which implies that tx minus ty equal to this is less than or equal to this. We can show directly by using triangular inequality that this is less than or equal to 1 over 14 x minus tx plus y minus ty. And what is this? This is d of x comma tx, and this is d of y comma ty, because we are using a usual metric on x. On the other hand, if we take y equal to 1 and x belongs to the set 0, 1 with 1 open, then we have tx minus ty equal to this, x minus tx equal to this, y minus tx will equal to 1 minus t of 1, which is equal to 1 minus 1 divided by 18, which is 17 by 18. Then consequently, we have tx minus ty equal to is less than or equal to this, and this is less than or equal to, again by using triangular inequality, one can show directly that this is less than or equal to 1 over 14 x minus tx plus y minus ty. What is 1 over 14? 1 over 14 belongs to 0, 1 over 2, and this is our alpha. The theorem is somehow parallel to the Banach contraction, that if we have a complete matrix space and T is a Kenan type contraction, then T has a unique fixed point. And for every x naught belongs to x, the iterative sequence will converge to x, to this unique fixed point. There is another contraction, which is a Chatterjee contraction, which is somehow similar to the, not similar, but somehow seems similar to the Kenan contraction. Here the difference is that we are taking a ty instead of a tx in Canaan contraction, and here we are taking a tx instead of a ty in a Canaan contraction. The theorems are the same, means that if we have a complete metric space and it satisfies the Chatterjee contraction, then there exists a unique fixed point. One other important contraction is the generalization of Canaan, and also Banach contraction is the Ricci type contraction, that if there exists alpha positive number alpha 1, alpha 2, alpha 3, such that its sum is less than 1, and it satisfies alpha 1 d of xy plus alpha 2 d of xtx plus alpha 3 d of yty. I said that it is generalization of Canaan and Banach, because if alpha 2 equal to alpha 3 equal to 0, then these terms disappear, and what we get is just this, that alpha 1 is less than 1, and this satisfy this condition, which is exactly the Banach contraction. The other on the other hand, if we take alpha 2 equal to alpha 3 and alpha 1 equal to 0, then this one will disappear. So if this is disappear and alpha 2 equal to alpha 3, then we can outside alpha 2, and we got this, which is exactly the Canaan contraction. Now, if the theorem is the same, that if we have a complete metric space and T is the Ricci type contraction, then T has a unique fixed point. One other contraction is the generalization of all the above contractions, which is important in the research purpose, for the research purpose, that if we have a metric space, then a map T is said to be Hardy-Roger type contraction if there exist non-negative real numbers alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 less than 1, such that its sum is less than 1, and it satisfies this inequality. Here you can see that if alpha 2, alpha 3, alpha 4, alpha 5, this is alpha 4, equal to 0, then we get Banach contraction. If we take alpha 1 equal to 0, then this is disappear. And if we take alpha 2 equal to alpha 3 and alpha 4, alpha 5 also 0, then we get Canaan contraction. But if we take alpha 1, alpha 2, alpha 3 equal to 0, then this disappear. And if we take also in the assumption that alpha 4 equal to alpha 5, then we got a Chatterjee contraction. So it is means more general than all the above contractions, and the theorems is somehow the same, that if it is a complete metric space and T is Hardy-Rogers type contraction, then T must have a unique fixed point. Sorry. Now I will discuss some generalization of metric type space. Means I have discussed that people are working I have discussed in the abstract that people are working in two different direction in metric fixed point theory. One direction is the generalization of contraction, or to define some new contraction type means. And the other direction is the extension of a metric space. It means that instead of a metric space, you use some other metric type spaces. One genuine and important generalization of a metric space was due to Szirvik, which we call B metric, that if we have a non-empty set and B greater than or equal to 0, a map DB is said to be a B metric if it satisfies the following three properties. The first two properties are same as a metric space. The third property is different from metric space property of triangular inequality. And instead of 1, we have taken that B is greater than or equal to 1. Now you can see that if B equal to 1, then it becomes a metric space. So it is means you can say that the collection of a B metric spaces is much more greater than the collection of a metric space. Here, if there, I will give one example, just non-trivial, that if we define from x to x, from R to R, from R cross R to R, a map D of x y equal to x minus y square, then this is a B matrix. This is not an example of a matrix space. The first two properties are very trivial, so I will not discuss the first two property. The third property, I have discussed it here, that d of x z is equal to x minus z square, which is equal to, just I have subtract and add y. Then I have used the elementary property of square, that this is belongs to this equal to x minus y square plus y minus z square plus 2 times xy ab. Now I have add x minus y square and also subtract, so it will not affect this equality. And also I have add y minus z square and subtract y minus z square. Now I have written this, that this is 2 times x minus y square plus 2 times y minus z square plus 2 times x minus y. I have written this means 2 times x minus y minus z here. And at the end I have written this minus and this minus y minus z square. Here I have taken 2 common, then this is minus, and what if I take minus from this, then we get that this is x minus y square plus y minus z square minus 2 times x minus y minus z, which is a square of this. Now we get this, and we know that a minus b is also less than or equal to a for all b greater than or equal to 0. Here this one is square, so this is greater than or equal to 0, and we can say that this equation is less than or equal to 2 times x minus y square plus y minus z square, which is equal to, which implies that dB of x is less than or equal to 2 times dB of xy plus dB of yz. Another generalization of this B matrix spaces was due to Pakistani mathematician, my supervisor Kamran, and its means colleague. They use some function s instead of b. Means let x be a non-empty set and s be a function from x cross x to 1 infinity. And a function ds is said to be an extended B matrix if it satisfies the following 3 conditions. The first 2 are same as B matrix and matrix. The third one is different. Here they used s of xz instead of b. But if we define a constant function s of xy equal to b for b greater than or equal to 1, then we get the definition of a B matrix space. They proved in the same way a theorem. Here I have not given an example, but you can say that this is means this one is also example of a extended B matrix, because if d of dB of x is less than or equal to 2 times d of xy plus d of yz, then you can write that this is less than or equal to 2 plus x plus z times d of xy plus d of yz. And here our define s of xy is 2 plus x plus y. Another contraction is I think Rizwan, we are short on the time.
Yeah,
Can
exactly. I was
continue?
trying to. If we can finish in 2 to 3 minutes, it will be great.
Okay. Then I think it is. I hope that this is the last slide. Okay.
Okay, thank you.
One another metric type space was due recently. It was by Nabil Malaiki, a Saudi guy, and his colleague. They used somehow different map by Kamran et al. They used the same map s from x cross x to 1 infinity, and instead of multiply s of xz to both the terms in the inequality, in the triangular inequality, they used separately s of xy to the first term and s of yz to the second term. You can see means now the difference between the previous one here s of xz, which depends on x and z on the left hand side. On the other hand, on the control metric, this s depends on the right hand side, means s of xy comma d of xy plus s of yz comma d of yz. They proved means the Banach contraction principle, and now people are working to generalize in different directions. They also give one another contraction, and instead of using one s, they use on the next paper two different maps, S1 and S2, means, and they said that this is a double controlled, means it means that it is controlled by S1 and S2, not just single function. And they use this inequality instead of the inequality in 3, and proved Banach contraction principle, and also the other, and also they used it in a different means integral equation, differential equation, and fractional order differential equation, and many more. So there, and also there are some other contractions, but due to time shortage, I will not explain it now. Maybe in the next I will explain, because it will need some background in the Banach algebras, and also what is spectral theory. So that's all. Thank you for the attendance and your kind. Okay.
So thank you, Wahidullah.
If you have some questions, then you can ask.
Yeah, the floor is open to the question. So go ahead.